Hello and welcome to Advanced Topics. In this section, we will take a look at recursive functions in Java and explore Big O notation to describe performance. Recursion to implement a Fibonacci function. In this video, we will learn the basics about recursion and then program several recursive functions to demonstrate recursion and, of course, the Fibonacci sequence. First, a few fundamental concepts about recursion. In programming, we use recursion to minimize the size of each step of a solution. As programmers, we always want to break big problems into smaller pieces. Recursion helps us with this. Recursion is simply the process of a method calling itself. There are benefits and detractors to using recursion, and often it is unavoidable. When done correctly, the code can be very compact and efficient. There are a few downsides to using recursion. It can make the code difficult to read and debug. It is also very easy to make mistakes. Let's look at the examples we'll be programming today. First, we'll print a line of text with a numeric reference of a given number of times, and we'll do this using recursion. And then we'll have two different examples to show factorials of a number. A factorial of a number is a product of that number and all the numbers below it. We're specifically talking about integers. So factorial 5 equals 5 times 4 times 3 times 2 times 1. And finally, the Fibonacci sequence. A Fibonacci sequence starts with a 1 or a 0, is then followed by a 1, and then proceeds based on the next Fibonacci number, which is equal to the sum of the two preceding numbers. And you can see the example on the bottom of your screen. So let's take a look at these examples in code. Start with the demo 1 class. And here we're just simply going to print text a specific number of times. And I set that up as an integer just called number of times. And we'll put number 8 in there. And then we'll call the function print text and we'll pass this integer to it. And then print text is our recursive method. Here it is. We're taking in the integer and then we're going to evaluate to make sure that the number of times is greater than 0. And then we're going to output a line. We're going to say print number and we're going to put the current value of that integer there. And then we're going to call the same function that we're in and we're going to pass to it an integer -1. So each time we recursively call this function, n times will be 1 digit smaller than it was previously. And when we finally get to it not being greater than 0, the process will end. So let's go ahead and run this. So you can see it ran 8 times, 8 through 1. Pretty quick, 11 milliseconds. Remember that number, 11 milliseconds, and now we're going to change the value 80. See how much longer that takes. So it went from 11 milliseconds to 13. And as I scroll up, you'll see that it actually did do all the work. Printed 80 times. So our first try was with 8, second try was 80. Try one more time with 100 as our final test for this class. We'll run that. It took 21 milliseconds. So you can see this recursive function is very, very fast. Okay, I'll clear that out. We're going to look at factorial. I'm opening demo 2, and we're going to show two different examples. Here we start with an integer called number to compute, and we're going to compute for 3. And here we're going to say the factorial of that number is, and then we're going to call this method factorial. This method is down here. See, it returns an integer and it's taking in the number of times that we established in the main class. So here we're saying if the number of times is less than or equal to 0, return 1. Otherwise, n times multiplied by, and we're calling ourselves recursively, n times -1. And then it'll keep going until we get to this evaluation being true. One thing I'll point out, if you see right here at line 24, you can see this little symbol, and it shows you that it's a recursive call. Just helps with troubleshooting. So let's go ahead and run this. Here we see the factorial of 3 is 6. We can certainly change that. Run it again. And you see it's quite fast. Okay, so that was a pretty simple example. We'll clear this out. We got one more factorial example here. This is very similar to the last one, except here I put this call in a for loop. And so we're going to, instead of having one line of output, we're going to have Here we should have 15 lines because we're computing until minus 16, and our recursive factorial function is not changed. This is just to show you a little bit more dynamic output. And I'll expand the output, and there it is. So you see it starts at 1, goes all the way through 15, and it only took 19 milliseconds. And this number is 2 billion. Okay, so for our last demo, we'll look at the Fibonacci sequence, and we'll open demo 4. This is our Fibonacci sequence. We're dealing with 3 numbers, right? The first one, the second one, and then the third one. We'll need that for calculations. And if we don't put a boundary at the end, this could go on forever. So we only want to display 10 numbers. And here we're going to print the first number, which, scroll up a bit, is 0. And then the second number, which is 1. And then we're going to calculate the Fibonacci sequence. We're calling this method, and we're passing it n count minus 2. So we wanted 10, but we've already taken care of the first 2 here. So we can start with the third one. And then here's that method here. So we're taking in the n count, and if the n count is greater than 0, then we're simply assigning the third number to the first plus second, and the first number to the second number to the third, and then we're going to output that third number. And then we're going to recursively call ourselves, decrementing the n count by 1, and that'll keep going until this statement is no longer true. So let's go ahead and run that. And there you can see 19 milliseconds. We can probably go a little bit farther. The interface here, let's just go 15 of them. You see the numbers start getting bigger. We'll go to 20. And you can see that it is somewhat time consuming. 20 milliseconds is not much, but we're also only calculating 20. If we did 200, see how long that would take. An extra 2 milliseconds. So you can see as I scroll in the output to the right, numbers are getting quite large. And then gets into scientific notation because they're getting so big.